who is going to talk about nonlinear regression in Virgo.
Okay, like that. Okay, transition. Okay, thank you. Okay, I have one. I'm going to share with you our work on Virgo data denoising using deep clean. Okay, let's start. Okay, since the first gravitational wave detection from a binary measure, up to now, over 200 similar events have been but many more events remain undetected because they are below this, the signal are below the surface of the noise, then could be detected if we can manage to reduce that noise. Okay, a large part of these noise come from environmental and technical sources. And many of these sources are already monitored by one or more witness sensor. To maximize the science outcome of the gravitational wave detector, we need to first reduce the sky localization area for a rapid multi-messenger follow-up. Secondly, we need to improve the signal-to-noise ratio. And then we need to detect more events. But anyway, for all of these cases, we need to reduce the noise. Now we have the problem. And the problem is the noise in the detector comes from many sources, some well understood and some still don't know. And these nodes can couple with the signal in a complex way. For example, in this picture from LIGO and 4 detectors, during the second observing one, we have the red curve is the major noise, and the black one shows the sum of the non-noise. As we can see, there is still a gap. That means not all the noise is accounted for. So this missing noise is a mix of environmental disturbance, instrumental artifact, and sometimes even the fundamental limits. So to improve the detector sensitivity, we rely on witness sensor. And that is where deep clean come in. Deep clean is a one-dimensional convolutional neural network designed to use the witness sensor data to subtract noise from the main gravitational wave channel. The main gravitational wave channel means here the readout of the detectors. Okay. So, unlike to the traditional epoch such as Wiener filtering, which is work really well, but only for stationary noise, deep clean is able to handle non-stationary noise. That is really very common to real detector data. So now let's talk about the type of the noise we can deal with. The data collected by the gravitational wave detector, denoted as h of t, can be written as s of t plus n of t, where s of t is the gravitational wave signal and f of t is the detector noise. And this noise is made up with the removable noise that is usually linked to the environmental and technical noise and the non-removable noise. And in Virgo detector, we have several thousand witness sensors which measure various noise. But how do we know which witness sensor to use for our training? For that, we study coherence with the h of t channel. Okay, for example, we have a coherence between a magnetometer at LIGO Livingston detector and h of t. And here, a coherence value of 0 means there is no correlation, and a value close to 1 indicates that this witness sensor can explain and use to remove that part of the noise. Okay, a typical neural network is like that. And in input, we have the initial parameter combined to some weight through layers and nodes, and we output the prediction. And we have the convergence of the loss function, which evaluate how well the model is learning during the training. Okay, really short, deep clean is help to reveal the gravitational wave signal by learning and removing what does not belong. Okay, that is the deep clean pipeline. We start with a set of a witness sensor data, which go through the pre-processing and prepare and normalize the data set. We use a down sampler in order to compress this data into a latent vector. And this latent vector capture the essential feature of the noise. Then a 4-layer upsampler use this latent vector in order to reconstruct the noise pattern. And then we redo another post-processing to be sure that we can remove that noise from the main channel. Okay, now let's talk about the data we analyze with Virgo detector. So we consider the data from all 3B observing one, and focus on total 2 days and 18 hours data. And we segmented them into a 4,096 seconds. Then we train each segment and use the first segment. If we train the first segment, we use the model of this segment and clean the until 100,000 seconds. Then we do another training. Okay, for our first step, we will focus on 3 frequencies. That's around 100, around 150 Hertz, and around 200, because we would like to remove the extra noise. Okay, as a result, we show here the amplitude spectral density before and after the deep clean process. Okay, the green curve show the original data, and the red one show the process after clean process. Okay, and the blue one is the ratio between both signals. On the right side is for the frequency band around 150 Hertz. As we can see, deep clean were able to remove a large part of the noise. Okay, now deep clean were able to remove the noise, but how this subtraction can influence the detector sensitivity? For that, we try to calculate the BNS and spiral range on each segment. So each dot represents one segment, and the green one is always the original data set, and the red one is the process after deep clean. So for the first frequency band, we note some increasement of 0.2 megaparsec. The second one 0.18, and the last one 0.02. So in general, we see that there is not a huge improvement in the BNS and spiral range for the single training. So we decided to use a multi-training process. And this multi-training process, that is a pipeline to help us to train on a large frequency band. Like in our case, we're training from a 15 to 415 Hz. So, and we use a sequential layers. The sequential layer mean here to training on a specific band frequency, the smaller band frequency. And in total, we use a 13 layers. And once we train the first layer, the output of this layer become the input of the second layer, and so on until we train and clean all the layers. And as a result, we show on the left side, we show the amplitude spectral density, and the green one is also the always the original data set, and the red one is the process after deep clean. And we can see where deep clean were able to remove the noise. And on the right side, we saw the cumulative binary and spiral range. So these curves show the evolution of the binary and spiral range through the layers. So the significant improvement were the layer 4, that's concerned the frequency band 55 to 65. Okay, to be sure that deep clean didn't destroy the signal, we decided to study the parameter estimation. And for that, we injected 128 binary black hole signal and use a one at a time process. That one at a time process is if we're looking for a mass sharp, we will retrieve this information by fixing all other parameters to their true value. And okay, here we have okay, for example, for the sharp mass, the blue color is the unclean one, and the orange one is the process after deep clean, and the green one is the zero noise. The zero noise mean here the pure signal, and the vertical line is the injected value. Okay, we plot here the plot of all 128 injection, and we can easily see the orange curve is all the time inside the credible interval. So that means deep clean didn't destroy the gravitational wave signal. Okay, in conclusion, you can say deep clean was already used in LIGO detector, and now we apply it in Virgo and show the similar performance. And in Virgo, we go on deep by using a multi-training process. We wish to improve more the result. And we hope deep clean will be adopted for the next observing run as a real-time noise abstraction. Thank you.
Okay, we have time for questions. Anybody? Yep.
Thank you for your talk. Okay, I don't know anything about this, but when you use deep clean, do you have to specifically target some of the spikes you see in the sensitivity curve, or is it agnostic to that and it will remove the noise throughout the entire observing frequencies?
Okay, if I casually question, we target a specific frequency band.
Yeah, exactly.
Yes, that's for the first time. Here we target a specific event. For example, for deep clean, it's really useful to have a smaller frequency band. Otherwise, if we trying to train a large frequency band at a time, we will not get a good result. So we need it. But the problem with the smaller frequency band, when we're trying to looking for the detector sensitivity, that don't increase the sensitivity. So for that is why we using the multi-training process, and it's the sequential process. We train on a specific smaller frequency, like the first one was a 142 to 162. And when we train, we clean it. So basically, when we clean it, we get these similar result like that. And then we take the output. The output is the clean one, and trying to clean the next layer frequency. So that means we doing a step-by-step, like a sequential process in order to train a large frequency band. For that, we can train like from 15 to, let's say, 1,000 and get similar result like if we was training on a smaller frequency band. But that takes use time.
Okay, thank you very much.
Any other question?
Out of curiosity, you said that the biggest improvement came in the 55 to 56 hertz band. So presumably from your witness sensors, you know what the cause of that noise is in that band. Is that right? Do you know what was causing the noise that you're now removing? And presumably because that can feed into future design, can it? Or
Sorry, can you repeat, please?
so
Can
you said that the main source, the biggest improvement was
Yes.
removing the noise at 55 to 56 hertz.
Yes.
So from your witness sensors, do you know what is causing that noise in the first place?
Okay.
I'm just
not-
curious, really.
Not really, because it's I mean a little bit magic thing with a machine learning. Sometimes, okay, we have some witness channel which measure a specific noise contribution. Sometimes maybe, but the problem with the noise, we have like a seismic noise, and we can have an electrical noise. We have let's say a magnetometer. But the problem sometimes those noise couple together,
Yeah, sure.
and so create another like non-stationary or non-linear noise. That's sometimes we cannot say, okay, that noise comes specifically from these sources.
Okay. So that correlation analysis you did at
Yes.
first showing none of those give a nice clear
Yes,
spike that
yes.
corresponds to what you're fixing. It's okay. Sure.
That sometimes if we were able to identify a lot of witness channel that is really coherent specific frequency band, the algorithm can be able to manage to reduce the non-linear noise by maybe the sum of all these noises.
Okay, fair enough. I thought it would be kind of cool if you could say, aha, this is caused by, I don't know, the frequency at which the system refills in the toilets or something, and then you could, look at design in future, but maybe not. Okay.
For example, that's why we know for the what we call the main power, like for Virgo is 50 hertz. That is because of the current. And
Okay.
for example, LIGO, that is 60 watt because of the power in the US. So that's why we know. But other one is sometimes really difficult. It's for that we use, because if we were know exactly where it comes from the noise, it was really easy to to remove it.
Yeah, that's it. I was hoping that your machine learning could
Yes,
kind of spit that.
exactly.
Okay.
Okay, so let's thank Weizmann again.
Okay, thank you.